Hello Year 11, it's Miss Bailey here. Please have your worksheet ready to be filling in as we go through this video. So to begin with, you've got 3 retrieval questions for your Do Now activity, all linking to the Haber process that we looked at last lesson. You have the equation for the reactions that happen during the Haber process, showing the nitrogen and hydrogen combining in a reversible reaction to form ammonia. So please pause the video whilst you have a go at those questions. So the word optimum means best. So when we're thinking about our optimum conditions, we're thinking about what was best in terms of both our yield of our reaction, so if considering Le Chatelier's principle, how quickly that equilibrium can be reached in terms of the efficiency of the process, and then also the cost of putting those conditions into place, because obviously this is an industrial process and companies are going to want to make sure that it is profitable. So the optimum conditions that were decided on was 450 degrees Celsius for our temperature, a pressure of 200 atmospheres, and the use of an iron catalyst. Now it is important that we note these conditions, the specificity of those conditions. For example, I'd seen in some worksheets high temperature, high pressure, but we do need to learn those specific conditions there. Where are the reactants of the Haber process obtained? And that is talking about where we're sourcing our nitrogen and our hydrogen from. So the nitrogen was from air, but we had to do a fractional distillation of air in order to obtain that nitrogen, whereas hydrogen we were obtaining that from methane, our natural gas, where we are reacting that with steam in order to produce hydrogen. So methane is obviously a fossil fuel. It's one of our unrenewable sources and therefore not a renewable source of hydrogen. And then the third question, what happens to the unused nitrogen and hydrogen gas? And they get recycled back into the reaction container so that they can continue reacting and so that we don't have any waste. So just to recap from last lesson, why the Haber process was important. So this was because ammonia can be used to make nitrogen-based fertilisers in order to replenish the soil. So what we're going to look at today is how we make fertilisers. So to start with, there's a bit of a recap from the topic you did back in year 10. So ammonium salts, these are formed from ammonia. Now ammonia reacts with water to form a weakly alkaline solution. So can you recall what the general equation for a reaction between an acid and an alkali is? Pause the video whilst you have a think. So it is acid plus alkali goes to salt plus water. So our ammonia here will be acting as our alkali in our reactions to form ammonium salts. And so this NH4 plus becomes our positive cation in that salt. And we'll look at those in a minute. So what type of reaction is it where we are combining an acid and an alkali to make salt plus water? Pause the video whilst you have a think. And it is a neutralisation reaction. So both salt and water are our neutral products, and whereas our acid has a pH below 7 and our alkali a pH above 7. So by reacting them together, we end up moving towards that neutral position with a pH of 7. So these, again, it's a bit of a recap, but looking at our ammonium salts. So here you can see that general form NH4 with an X, and that X depends on the type of acid that we use. So the type of ammonium salts that we're going to come across is ammonium sulfate, ammonium nitrate, and ammonium phosphate. And they come from sulfuric acid nitric acid and phosphoric acid respectively. And so those X components, the X anions in the salts, they are the sulfate, so SO4 2-, nitrate, NO3-, and phosphate, PO4 3- respectively. So what we're going to be considering is how we are going to go about making these salts from the acid stated and ammonia. So ammonia is our NH3 that we looked at on that previous slide. So can you now have a go at writing the word and balance symbol equations for the reactions of ammonia with each of the different acids that we looked at on the previous slide? So pause the video whilst you have a go at those. So the key bits that I want to pick up from this is just what our salt formulas are, because we need to make sure we're getting the right ratio between our 1+ ion and our varying negative charges. So with our sulfuric acid, we're going to be forming ammonium sulfate. So ammonium has a 1+ charge, whereas sulfate has a 2- charge. But we need it to be neutral overall, as you can see here. And so we're going to need another NH4+ in order to counteract that negative charge. The +1 + 1 - 2 adds to make 0. So we always need it to make 0. So we're going to put the NH4 in brackets and a little 2 after it. And that 2 tells us we've got 2 lots of everything in those brackets. And then SO4 is our sulfate component. With our nitrate, that has a 1- charge, and therefore we're going to only need one of those NH4s because +1 - 1 is going to make 0. So for nitric acid, we're making ammonium nitrate, NH4, NO3. And then phosphoric acid, this has a 3- charge. So like with the sulfate example, we're going to need multiple ammonium ions to balance out that 3- charge. So in this case, we're going to need 3 ammoniums because that will give us a +3, and then PO4 is that phosphate part. So those are the formulas for your symbol equation. I will just stick the acid ones here as well, and hopefully you can then go through and correct anything that you didn't get. Do make sure that it's balanced, so the same numbers of atoms on each side. So we now have a couple questions for you to be thinking about. Pause the video whilst you try and think about those. So these are the answers to those questions. So we need the fertilisers to be liquids or soluble so that the plant roots can absorb the fertiliser and therefore get the nitrogen that they need. However, solid fertilisers are much easier to transport. Now, a formulation we looked at in our chemical analysis topic, and that was a substance created for a particular purpose with different molecules mixed in. So with our fertilisers, we're going to be combining different salts for the particular purpose of helping those plants to flourish in the field. Which elements have the symbols N, P and K? So we can see that on our periodic table that they would be nitrogen, phosphorus and potassium. So nitrogen and phosphorus both being in group 5 and potassium in group 1. And then a titration, so this is something that you will have looked at last year. So this is a method of investigating what volume of an acid or alkali is needed to neutralise a volume of an acid or an alkali. Now we've been looking at neutralisation reaction in order to make our ammonium salts. Acid plus alkali goes to salt plus water. So titration is one way in which we can make sure that we're doing this accurately. So can you please have a go at filling in what NPK fertilisers, which 3 elements are they going to be containing? Pause the video whilst you have a go at this. So we don't actually have compounds which contain all 3 elements, nitrogen, phosphorus and potassium. So we have a formulation of compounds which are going to provide all three of these elements. So to start with, we can consider where we get our phosphorus from. So this is a phosphate rock which can be mined from the ground. This phosphate rock is insoluble in water, and so to overcome that problem, we treat it with acids. So depending on the acid that we use, we get a variety of different outcomes. So if we use nitric acid, we get phosphoric acid, but we also get calcium nitrate. If we were to use sulfuric acid, we would get a mixture of calcium phosphate and calcium sulfate. And then finally, if we were to use phosphoric acid to produce calcium phosphate, and then finally, if we were to use phosphoric acid, we would produce calcium phosphate. To get our potassium, we would have our potassium chloride or potassium sulfate, which again can be mined from the ground. But these are both soluble in water, and so we can use them directly. Okay, so I have 4 questions for you to have a go at if you pause the video whilst you complete this. So the next activity is summarising those different salts that we were talking about. So this diagram has arrows showing what we are using to produce something else. So phosphate rock, this is going to be reacting with one of our acids to produce some salts. But if we react the phosphate rock with phosphoric acid, what do we get there? If we react it with a different acid, which salt are we going to make there? How do we make ammonia? If we are using ammonia to make one of the acids, and then reacting ammonia with that acid, what would we get? If we react ammonia with phosphoric acid, what salt do we get? And then what's our ultimate product here that we're trying to make? So pause the video whilst you complete this in your worksheet. So this is the answers. The crucial bit is identifying nitric acid. So ammonia can be used to make nitric acid, and that nitric acid, when we then react that with phosphate rock, we can produce our calcium nitrate and our phosphoric acid. When we react it with ammonia, we end up with ammonium nitrate. We can react our ammonia with phosphoric acid to produce ammonium phosphate. And we can react our phosphate rock with phosphoric acid to produce calcium phosphate. And we can react our phosphate rock with sulfuric acid to get the calcium sulfate and calcium phosphate. So nitric acid can be made from ammonia because you will note that they both contain nitrogen atoms. So what we're going to be thinking about now is a bit about how we actually go about making them. So in the lab, this is our titration setup. So we've got a burette here filled with dilute sulfuric acid and our ammonia solution in a conical flask. So by doing this setup, we can make sure that we are adding accurate amounts of our sulfuric acid until we get to our end point where it's neutral and we would have ammonium sulfate produced. We would then take that solution of ammonium sulfate and we would need to evaporate off the water that was produced as the byproduct. So we do this to the point of crystallization, and so this is when the solution becomes saturated and we start to get crystals around the edge. So question for you to recall, thinking back to titrations. How could you determine the end point of this neutralization? So when we've done titrations previously, we will have put an indicator into that solution. But given that that's where our product is, are we going to want to be adding an indicator into the solution? What could we do alternatively? Pause the video whilst you have a think. So we could use litmus paper. So what we could do is we could take a glass rod and stick it into the solution. We would then get a drop on the end of the glass rod, which we could then put onto the litmus paper. And then looking at the colour that the litmus paper changes, if it changes at all. So we would want to test with both blue and red litmus paper to be able to identify that point of neutralisation. So what I'd like you to do now is you have some information, and I've put this picture onto the Padlet so you can make it larger, is to compare our in-lab process to our industrial process. So the table has been drawn out for you on the worksheet already, and there are sections to be commenting on each of those factors. The majority of the information you'll need is in this picture. However, you might also find it useful to do a bit more research on BBC Bite Size. Thank you all for watching. See you next time.